Before we get into the details of the four types of filters that we'll be examining throughout this course, I want to focus on what is a first order filter a little more. As you already know, a first order filter is one of the simplest types of filters. It uses a single reactive component, which is a capacitor in an RC filter or an inductor in an RL filter, and that's paired with a resistor to shape the frequency content of an input signal. The term first order comes from the fact that the mathematical description of these filters involves a first order differential equation. This simplicity leads to a gradual transition between the pass band and the stop band, which is typically with a slope of 20 decibels per decade. So you might be wondering if you need to learn how to work with differential equations to understand first order filters. And the answer is no. While first order filters are derived from linear differential equations, a student can understand the behavior and practical use without needing to solve such equations. You will need to know basic algebra, understand the concept of frequency phases, which you will learn more about in this course, and basic circuit laws like Ohm's and Kirchhoff's laws. The main attributes of a first order filter include single energy storage element, where only one capacitor or one inductor is used, the time constant, which is the response of the circuit, which is defined by the time constant. In RC filters, the time constant is given by this formula here, where the time constant tau is equal to R times C, and that's in RC circuits, where in RL filters you have tau equals the value of the inductor divided by the value of the resistor. Then we have the cutoff frequency, which is the frequency at which the output signal falls to 70.7% or minus 3 decibels of the input. For RC circuits, we've got this formula here that allows us to calculate the cutoff frequency, where Fc is equal to 1 divided by 2 times pi times R times C. And for RL filters, the formula is Fc for cutoff frequency equals R divided by 2 times pi times L. Then we've got a gentle roll-off, which is a characteristic of a single order filter with a slope of plus or minus 20 decibels per decade. The filter gradually attenuates frequencies beyond the cutoff, unlike the steeper slopes seen in higher order designs. First order filters use a single reactive element, as you already know, and that results in a smooth transition between passed and rejected frequencies. In contrast, second order or higher order filters incorporate two or more reactive components, and this leads to a steeper roll-off. Second order filters typically offer a roll-off rate of 40 decibels per decade, providing a sharper distinction between the pass band and stop band. There's also more complex response characteristics. Higher order filters can exhibit resonant peaks and more pronounced phase shifts, which can be advantageous in applications requiring precise filtering but add complexity to the design. You might be wondering here, what exactly is roll-off? So roll-off is the rate at which a filter attenuates the signal amplitude beyond its cutoff frequency. It is typically measured in decibels per decade or per octave. Now here I've got a table that summarizes the main attributes of common first order filters, and I'll let you have a look at it for a few seconds. Just keep in mind that in these expressions, the letter S represents the complex frequency, where S equals J times omega, where omega is the angular frequency in radians per second. And again, if this is not familiar or you need a refresher, have a look towards the end of the course, where I have a primer on the algebra that you'll need to understand the mathematics in this course.